Welcome back to Eulerville. So we will be continuing our discussion from part one with our projectile motion formulas. We will be discussing things like the max height, the time of flight, the range, and the trajectory equation under some cases. So that's about it. Let's start. So first up will be the time to reach the maximum height. So, whenever we throw something or an object into the air, um, it seems like it can just uh, go up forever, right? But the thing is, gravity exists, and there is a time there will be a time where the object reaches its maximum height and then it falls off. That is due to the direction of of gravity, which is downward. It's opposite the way up. So um the question is, when does that happen? When does the gravity win in this tug of war? All right. So first is it is very helpful to name things first before solving. Um uh we first look at the initial velocity. Uh we have here our components, the 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 v naught cosine theta for the x direction and the v naught sine theta for the y direction. Okay, so it is inevitable for that object to reach its maximum height. But then after that time, um, the object will now go down. Gravity has won. But when does that happen? So we will denote that time as P sub up. Okay, so we will get that formula from our past video, which is uh, the velocity in the y direction, given that we have a acceleration, non-zero acceleration. We have no a constant acceleration. I mean, so based on this formula, which is v sub y equals v naught y plus a sub y t, or time, um, which this implies that the acceleration is constant, uh, we can solve for t sub up. So the conditions for t sub, t sub up is or are um, the velocity in this time, in the specific time, is zero, because it is at its peak. The the object is not moving, so its velocity is zero, and v naught y is the y component of the initial velocity, which is v naught sine theta. And the acceleration, the constant acceleration that I'm talking about, is nothing but negative g, or negative 9.8 meter per second squared. And t is t sub up, which is what we're looking for. So plugging those in our formula, we get 0 equals v naught sine theta plus negative g t sub up. And then rearranging to get t sub up, we get v naught sine theta equals g t sub up. And then dividing both sides by g, we get t sub up equals v naught sine theta, giving us the time that it takes for gravity to win uh, to take over the direction of the object's movement. Okay, so that's it. Next up will be our maximum height. Okay, so if we have a time such that the gravity wins, it is also natural to question what is the value of that maximum height for which the time uh, provides when gravity wins. Okay, so um, we always start with our initial velocity and breaking down its components. So um, in the x direction, we will always have v naught cosine theta, and the in the y direction, we have v naught sine theta. And then um, we are trying to find this uh, height. Okay, so we could plug our t t sub up. We could plug this t sub up, which is v naught sine theta over g to our time dependent equations for the y position, but that takes time. That is why I introduced you to the time dependent equation for uh this kinds of problem, since this height is essentially just uh, a position problem. Then we are also given the acceleration and velocity. We can find this using this general formula, which is v square equals v naught square plus 2a delta x. But in the y direction, we will have to translate that. So in the y direction, the v becomes v sub y square, and the v naught square becomes the y component of the initial velocity square plus 2 times acceleration in the y direction times uh, delta y. So instead of delta x, which is just a general position, general change in position, we are looking at the y direction, the change in y position. So this is all due to the acceleration being constant. So this wouldn't work if the acceleration isn't constant. So that's just a reminder. Okay, so for our objective, which is to find this maximum height h, we will have to know our conditions. So in this uh, time, uh, in this moment, the v sub y is 0, since it is at its peak, as I said before, and v naught y is v naught sine theta, and acceleration in the y direction is nothing but negative g, or negative 9.8 meter per second square, and this change in position in y direction is h. So yeah, it's pretty obvious, since this is the position and this is the initial position. So uh, and it is literally this length we are trying to know, then change in y should be h. So plugging those to our formula, we get 0 square is equal to v naught sine theta square plus 2 times negative g h, and rearranging, we get v naught square sine square theta equals 2gh. And then dividing both sides by 2g, we get the maximum height, which is um, v naught square sine square theta over twice the uh, acceleration due to gravity. Okay, so that's it. And now we will be looking at the total time of flight. Okay, so for this uh, specific case, we will consider the object starting from its initial y uh, position and landing in the uh, same height. So for for us to get the total time of its flight, notice that the time it takes for the object to reach the peak is just equal to the time it takes from the max height to the bottom, bottom position. Okay, so by symmetry, put into a bit of equation. So the time, yeah, as I said before, time for uh, time for this condition uh, equals the time for, yeah, this condition, which is just like rotating the same thing. Okay, so with that, uh, from our from our formula in the first part of this video, uh, the time it takes from y equals 0 to y equals h, which is the maximum height, is t sub up. And t sub up is what? V naught sine theta over g. So since we are looking at the total time, we just add them both. So that's 2 t sub up, and 2 times t sub up is just uh 2 v naught sine theta over g. So that's it. Now we are gonna discuss the horizontal range. So this answers the question that while we were traversing this trajectory, how much horizontal ground, did we cover? And that is given by r, or the range. So since the x velocity is constant throughout the motion, the identity that the velocity in the x direction is the derivative of the x with respect to time, it gives us that x is uh, vx t. Technically there would be a plus c here or a v naught here. Oh, no, x naught here, but we just consider that as 0. So yeah, in this case we just consider that as 0. So also, uh, since Vx from the start of the motion is V not cosine theta, so all throughout the motion, uh, V not cosine theta is indeed the velocity. So therefore, x is given by V naught cosine theta times time. So for our the conditions are x equals r, since since um, since since this distance is r and our x here is 0, so r minus 0 is still r, as it is the change here. So x equals r, and the time t is equal to the time covered. So that is 2v naught sine theta over g, as it is still the same scenario we discussed earlier. The object starts and ends in the same height. So the time it takes is indeed 2v naught sine theta, and plugging it in to our formula, which is this one, we get r equals v naught cosine theta times 2v naught sine theta over g. And simplifying that, we get v naught squared times 2 sine theta cosine theta divided by acceleration due to gravity. But we have an identity to make this simpler. We have that trigonometric identity that sine 2 theta, or the double angle, is given by 2 sine theta cosine theta. So all in all, we have the range given by v naught square sine 2 theta divided by the acceleration due to gravity. Okay, a follow-up question though. So, if um if we fix this initial velocity, uh, what is the maximum angle that we can um, use to maximize the range of our object? So the sine function, the sine x function, its maximum is 1. It's always less than or equal to 1. In fact, its ranges from -1 to 1. So the angle that gives that is 90 degrees. So since we have here 2 theta, 2 theta equals x. So 2 theta equals 90 degrees, and therefore the maximum angle we can use for maximum range is 45 degrees. So that's a very good addition. So yes, that's it. So finally, we will do the uh, equation of trajectory. So this is very useful when, okay, so picture this. You just see falling, oh no, an object in projectile motion. You are somehow given its velocity, its um, angle in angle for its initial velocity with the horizontal line, and its y and x positions. But how do you how do you do how do you do analysis of it without dependence in time? So how do we become time independent? Okay, so for that to happen, we have to recall that from x equals v naught cosine theta t, we just isolate time actually, and that gives us t equals x over v naught cosine theta. So it's still the same trajectory. but we are not depend we the mission is to not depend on time. So yeah, so it's like treating the trajectory as a parabola, as a regular parabola, like this one. uh, the y, x, and right here. You know that those familiar uh, math lessons in high school. So for this, from this, since y is given by um, v naught sine theta t minus g over 2 t square from the last video, um, there should be a there actually should be a y naught here, but I'm just considering that to be zero, so we can just ignore that and focus on the main equation. So what we're gonna do is just plug this expression for t, substitute for t. So what we get is a pretty long um, expression, but uh, um, this cancels out, cancels, and sine theta over cosine theta, that's very basic. That is tangent theta. So the second term is, we just simplify that. You get gx squared over 2. Oh, there should be a 2 here. I am sorry. Okay, so yeah, uh, we now have our um, equation of trajectory. So with this, we can just have our angle, our x, and we can know what y will be in any projectile motion. You don't need time, okay? So well, as long as you provided x and angle, of course. So yeah, so that ends this um, video, and I hope you now have a pretty strong grasp of where these formulas being thrown at us are coming from, instead of just um, blindly uh, uh, using them. So next up, we will be doing problems, and yes, things will get more fun here from here on. So that's it. Goodbye. This has been Eulerville, and take care.